So Odem, you're going to explain to us about abstract generation and making LEFs, and then Slava, where you can, please point out to us how this affects the full chip and what we should make sure that we pay attention to, and also Odem, try to tell us what to do to ensure that our abstract came out in the correct way before sending it on to the backend team.
By the way, Slava, you have a document, right? Also for us?
It was written like maybe about 2 years ago, 1.5. So maybe it's not fully relevant, but in general, there are some ideas that are applicable, and some of them are less because they are more inclined to the macros that are delivered through the digital tool and not through the custom. So it's a mixture. So not everything there is relevant.
So maybe we can take an update and combine even the two things and get something that's really good in the wiki or whatever. Okay, so let's start. Odem, you're going to take screen sharing.
Yes. Okay, do you see the presentation?
Mm-hmm.
And now it's the correct one?
It's the one with your face, right?
Yeah, it's the LIB and LEF guide.
Okay, so as Adi said, anyone who knows anything about this can interrupt me and help me because I'm not sure I know everything 100%. So any comments will be good. So I tried to make a guide of the steps that you need to do to actually make the LEF with extra pointers for giving the final file to Slava, because these are the most important things. And actually I did write like the how to check before you actually send it. And this is just like a brief tutorial. I need to still fix things. So if comments about the slides or things that aren't explained really good, then tell me and I'll make a better one. So I will start with talking a bit about the lib. It's not that important. I'm just going to talk about what you need to do in the lib file so you can make the LEF. So in general, the lib file is, as you know from Adi's courses, it's the timing model. Of every corner, you have all the information that you need for the timings. And they calculate the propagation delay, the output transition, the setup and hold, the data retain, and so on. These are all the things that you also need to send when you want to send your IP to tape out. So the things that
What
we have...
What is the data retain? Sorry.
Data retain is how long the data is still valid before the next clock cycle. So you have like an output and you have this, and you can sample it until the data retain. The data retain is the time until it's corrupted and you can't read it out.
Okay, thank you.
So just to add to that, it's only relevant for things such as like an SRAM where you latch the output until you maybe do some sort of pre-charge or something which will corrupt the output data. But it's not relevant in things like standard cells, so we didn't discuss it in previous courses.
Okay, thank you.
Yeah, that's what I wanted to say. Every lib file will probably look different according to what block you're making. So we need to define these properties, all the timing properties. This is things that you can do with your own cell after you finish the design and you run simulations, most probably on post-layout simulations, just that you know what your setup and hold and all the timing properties. And you need in the lib file to, I'll show it in a bit, to define all the power pins you have. Supposedly you should know what the names are, all the input and output pins, and buses if you have buses. So you need to know what are the buses and what the lengths are and what the names of these pins are. So here's an example of the lib file. So what's important, second. So you have the cell definition. You need to know the name of the cell that's written in Virtuoso in your design. And at the beginning, we define all the power pins. So you have VDD, VBoost, and so on. And then you have all the regular signals, the pins. And you have the direction and the related power pins, the ground and power, which have to be exactly the same as the pins you defined here. They can't be different. And if you have buses, you also need to define the buses and the length and everything. So this is just an example. I can also upload a template so you know what to fix. And at the bottom, we have for each pin, you have all the timing properties, the fall constraint, the rise, and so on.
Odem, maybe just another word about this. So what Odem is showing here is a kind of a methodological problem or approach that we use. The problem is that we have created most often these types of files by hand. We manually go map out what the different constraints and so forth we want to put into the tables are, and then we run simulations and fill them in. And then things like you see area and cell leakage power and so forth, we fill in by hand. Actually, there are tools for doing this, for automating this process, which if you can get them to work, then it's a much better way to do it. So for example, Liberate MX is for doing characterization of memories, but it's hard to use if you don't have a very specific memory structure. And Liberate AMS is for doing analog mixed signal design. So if you have just a generic custom block that does something that's not a standard cell and not a memory, you can define test benches and so forth, and it should be able to extract and write out your lib file. So if you can get the tools to run or write your own tool, because sometimes it's even easier maybe to do that because the tools don't seem to work too well, then that is something that can be done rather than just doing what Odem's showing here, which is writing it basically by hand.
Yeah, so this is a template that Robert once wrote, and from then I passed it on for the current chip for Sansa. I also sent it to Inbal, Netanel, also Andrada from Switzerland, and they just used this one and changed the name of the pins. And the problem that Slava talked about on the last meeting was that they had a related pin of clock. They just needed to put something here even though they don't have a clock. But this is just a template that I have, so probably we can delete things or change them, but we just don't know how because we're using this this basis for everything.
One more comment.
Yeah.
I think that the lib file has actually a huge header that you don't show in here. So the libs defines the default process node, the default corner, a lot of tables like 5 on 5, 6 on 6, a lot of stuff that you don't show in here. It's right.
Yes, exactly. I just wrote it down to
all
add
of the
it here.
things that here it's only a cell, but the lib file has a big header.
Yes, exactly. It has a lot of other parameters there, and I just wrote to myself to add it here so I can show it.
Okay.
Okay.
Though on that level, I would say, Slava, that probably is best to try and use a similar header or to what is in the standard cell library. And even
Yes,
in fact,
of course.
say,
I just stating that somebody will open a lib and see like a file 1,000 times bigger. He will start questioning questions.
Yeah, of course.
but maybe to emphasize what Odem said before, in general, as engineers, we should never use a template without understanding what it does. And yes, this template that Odem has is good for exactly our EDRAMs with the specific interface they use and how they work. And if you're doing a different block, you can't use it without knowing what it is and adjusting it. It might not be so easy to adjust, but you have to understand it and adjust it to have the right functionality.
Actually, one more comment. What Odem shows here is a lib characterized for a single corner. Okay, so like maybe she characterized it for a single corner, but I guess she took into account some like very big margins and she plans to use this lib across all the corners, but including this big margin, safety margin, because the tool, when the place and route tool or a synthesis tool, uses a lot of liberty files, like intended for each corner, temperature, and so on. Here we see only a single example.
So,
Yes.
so Slava, what you're saying is that a macro provider should make a file like this for each corner, and
It's basically a lot of work. So maybe the approaches should be like what Odem and Robert did, like include some huge margin that will used as a safeguard.
Yeah, so that's exactly what I did. I simulated on all the corners with different temperatures, and I just took the worst case, and that's what I detailed here.
It's suboptimal, but it's too much work otherwise.
Yeah, we can make 4 different lib files for each corner and just update the timings. But this one, it includes the worst case.
Okay.
Okay, I'll mention that also. Okay, so a few important notes. These are things that are important for the abstract generator. So you're supposed to know, you probably know the name of the pins, also the power and the signals. The names have to match exactly the ones that you will have in your layout. And you can't write pins in the lib which aren't in the layout, and the other way around also. You can have pins in your layout that are in the lib. And the file can also be written in a .lib version or a Verilog file. Both are fine. We just write it in the lib. And you need to make sure that the cell in Virtuoso, the cell name and the library name appear exactly as they should in the lib file. So now we'll talk about the LEF, which is the most important thing. So just in a small introduction, as you remember, the LEF is just a high-level representation of the layout. This is what Slava needs for integrating our block. He needs to know the dimensions and the pins and everything. And they know what the layer types are, the vias, the pins and blockages, and so on. So the final LEF is the one after we finish our design and simulation and everything, and we finish our layout. This is what we deliver. But Slava can't wait until we finish everything. So a couple months before the tape out itself, there's already a floor plan process. So we need to generate an initial F. Just for an estimation of the area, usually according to what the SOC tell us, what kind of estimation we need, if we can be correct within 50%, 70%, just to know the approximate size of our block. And the pins, hopefully we already know what pins we need, how many pins, and also their placements. So I will talk mostly about generating the initial layout, which is the one we'll extract for the initial F. And when we finish the final layout, it's the same process as this one. But for the initial layout, there are a few things that we need to know before we do this. So well, I'll talk in a bit about the abstract generator. The abstract generator is the tool that creates our LEF. So it operates on a layout. So all we need to do is just open a layout view in Virtuoso. And we don't even need a schematic or anything, just a layout. And the abstract generator, it just searches for different layers, only the layers that are actually fabricated. So text layers or rulers, they don't really matter at this stage. And it just searches for these layers and translate it to polygons. So what we need for the initial F, as I mentioned, Slava needs to know just the size. He needs to know approximately how big our block is. And the power grids, because also the power grids are the things that he integrates, and we need to connect with the power grids to our block. So
actually, there is one more thing, but it becomes less relevant in more advanced nodes. One more thing is like the directions that the macro could be rotated. It's also in the LEF. It could be, for example, mirrored across y-axis, x-axis, or maybe rotated even 90 degrees. So the 90 degrees rotation is already irrelevant in 60 nanometers, but beforehand it was possible too. So this info is also in the LEF, and we should know it also in order to know.
It's called symmetry in the LEF.
Yes, exactly.
Yeah, but
otherwise the tool won't be able to rotate it for optimizations.
okay.
Yeah.
So for just the initial layout, even if we don't have anything yet, we can just choose any type of layer. It really doesn't matter, just to create the frame of the block according to the dimensions we know we need. And the power grids, I'm not sure if we always need them at this stage, at the beginning stage, but if we know the power grid, so also just add all the stripes, and they must go from edge to edge because this is how they will be connected at the top. And the last thing we need is also the input and output pins, which are also must be placed on the edge of the block on the boundaries. So the pins are, they have some important properties.
Why do they need to be placed on the edge?
Because this is how we connect to them from the outside.
Power pins.
Actually, this is not a must, but we want to leave to the tool less possibility to do stupid things, because when they're on the edge, the tool doesn't have too much choice and connects from the edge. When the pins are in the middle, the tool can consider multiple ways how to do it, and for sure he will do an error.
You're talking about power pins or
no signal pins? Power pins should be.
But if you look at the library, it's very common that pins are
power pins.
No, this is different. You are talking about standard cells, because when they plan standard cells, you are correct. The pins are in the middle, but in standard cells it's a little bit different. I don't know all the details, but first of all, they do a great planning. Like it can be, for example, on the two last tracks from bottom or top. It can be too close to the edges. There are some constraints in order to the router be able to access these pins. And when the thing's not planned well, the creepy stuff starts to happen.
So, but I think what's important is to make them signal pins, to make them cross the tracks. But what is the benefit of the edge?
Wait, Udi. I think again, what Slava's saying is you're mixing up two things. Standard cells is not this lecture. Standard cells is a different lecture that we have in the course, and it's much more structured, I would say. And there you put the pins in the middle and so forth, and only on like a metal 1 or something layer, you don't use any metal 2 and so forth.
So
here we're talking about SRAMs or other blocks, and these blocks, if you put the pins not on the boundary, it causes it's not good for the router. The router doesn't like it, and it will often cause all kinds of problems that you don't want to deal with.
You're talking about macros.
But I will say that power pins should be fully extracted, so they should be on the internals as well. Correct, Slava?
No, like it could be, but it's too much. I think it's sufficient that only the main power rails will be exposed. You don't.
Yes. I mean the top level.
Yes. Maybe top 2 or top 1. Yes, but not all of them.
Yeah, that's what I meant. The top level should, so you can drop vias from the power grid that goes above it. Unless you're putting a ring around, and then actually the boundaries are enough, right?
Yes, yes. But if you have them exposed, then you have the most flexibility. You could do a ring, you can do vias from top. You have all the possibilities from the top. When you do it on the boundary, you actually confined to a ring.
Correct.
Odem, will you show how to remove the bottom layers, like the details of from them?
But maybe it's more relevant for the advanced LEF.
I don't know, but I always wanted to know how to do this.
Wait, let's continue and then ask these questions.
Yeah, we'll get to it, to the extract level. So the last thing, as mentioned, we need to also place the signal pins. They must be at the layer type of pin. Whoever plays with the layout knows what I'm talking about. And we also need to place underneath the pin a metal layer of the same layer. Because when we do the extraction, then it needs to know the whole stripe where it's placed. And of course, we have to have the same name as detailed in the lib or RTL or whatever. It needs to know the exact same names. And the last thing we need to do to finish our initial layout is just to move the origin to the lower left corner. And this you can do from the edit and the advance and move origin. If we don't move the origin, it will just think that the origin is the lower left corner of the macro we just placed, and it won't be 0, 0 probably, and then we'll have to go back and fix it. So this is just to show you what I meant about the pins and powers. So we can create the label, the pins using the label pattern and selecting the layer to be M3 pin and just place it on the boundary. And underneath we'll have a metal 3 drawing layer. And here's an example of how the power stripes could look. They're also from the boundary and they go from the top to the bottom. And they have the pins that they need on them. And here you can also see that the origin is at 0, 0. And now I'll move on to talking about the abstract generator. So as mentioned, it's the tool to create the LEF files. The inputs are the layout. This is the layout that we want to place in route. And we also need the lib file that we talked about earlier. And the output is just a .lef file that this is the one we need to send. Okay, so I'll talk about the tool itself. What are the stages, and at each stage what's important to know. So we need to open the abstract generator from the workspace. It needs to be the same workspace as where the library is. So it will open this interface, and these are the flows. These are the stages we need to go through. We'll talk about each one of them, but you can go through the stages with these icons, the pins, the abstract, the extract, and so on, or just by going to the flow tab and checking each step. But it won't let you continue to a stage if you haven't finished the previous one, because they're based one another.
A small question maybe to Adi. Adi, do you know if there may be more modern version of this tool, because it looks like 20 years old? And
as far as I know, about 15 years ago, I said the same thing to Cadence, and it was 15 years old then, and I don't think there is, no. It looks exactly the same as it did 15 years ago.
Okay.
So the first step, which is the easiest one, is just to import the layout, because it needs to know on which layout we're working. So with this library, with this book icon, we can just press on it, and then it will let us, it will open up all the libraries from the workspace. And then we just need to check the cell we want to work on and move it to the block. This is also important. People usually forget about this. The default, it comes in the core bin, but we are not creating a core. We need to work on the block. So after we stand on the cell that we were working on, we just need to go to cells, move, and then choose block.
So Odem, I mean, you said something here in just a little bit of background about that, and maybe Slava will help me with this. So in your LEF, you have a class. There's the first thing that it says about each cell is which class it is, and there are classes such as core, block, and maybe some other things. And that is a difference between, for example, standard cells or other types of macros. And this causes all kinds of things when you're doing like special routing or just general routing. The tool, at least the cadence tools, they really use this class core or class block to decide what they're allowed to do. And if it has that wrong word, it just won't work, and you really pull your hair out trying to figure out why. Slava, you probably, I haven't dealt with it for a while, but you probably can elaborate on that.
I guess you are right about the routing, but for sure there is a effect on placement, because blocks have different placement constraints rather than core cells. Core cells must be aligned to core site, which is the minimum standard cells existing in the library, which has some standard cell row height and some minimal width. Regarding the blocks, there is a placement grid which is completely different, which is like more granular. So it's easier to place a macro than a core cell. This is what I know about the placement. And I guess it's also related to routing. Yeah.
So what Odem is saying here basically is that you have to, in this GUI, you have to move your cell into the right category, or else it comes out with the wrong word in the LEF file. Basically, everything we do here, it affects what is written in the LEF file in the end.
One more thing, that sometimes we do some database commands like get db something and looking for some specific stuff. So example, if you don't put IO or put a core instead of it, it will not find it, the tool, because it's not of an IO class, for example, or core or block, whatever. But sometimes we do database commands, database search commands. So it's one more thing to consider. A less important one, I think the most critical is the placement.
Okay, Odem, continue.
Okay. So the second step is just to import the logical. The logical is the lib file. So we just need to import it and choose here lib, if it's of course a lib file. And it probably won't work on the first time. Beneath, I didn't show it, but here at the bottom, we have a bigger window, which is the log of every step. So in the log below, we can see the process and make sure that everything is correct. But if not, it shows warnings or errors, and it's not that clear, most of the errors that are shown there, but we need to make sure that the lib is imported, that it's imported correctly before moving on. And we can also see there that the pins are created. The most important thing here is just the pins.
So just one more word about that. So again, what this stage is, if I understand correctly, is that the abstract generator wants to know what the actual pins and labels are that it should make pins in the, or I think it calls it ports in the LEF. So it can either extract it from different formats. The one you're going to be providing a lib and a LEF anyway. So usually you read that out of the lib file and it will look for the pin names in the lib file. But you can also, sometimes it's faster at an early stage just to provide a Verilog, like a wrapper that shows the names of the pins and their directions and so forth. So you can provide a Verilog instead of a lib file at an early stage.
Yeah, exactly. So here, it's not exactly there's another stage after this, which is the pins, but here it makes sure that every pin you wrote in your lib file is also appears on the layout, because they have to match the lib file and the LEF. So here I wrote about the most common problems that happen when you don't get this green V on the logical step. It's almost always problems with just the pins. As I mentioned already twice, that the pins might be in the lib but not in the layout. And sometimes there can be also syntax errors in the lib, just a comma not in the right place. And these are very hard to debug because they're not detailed, but hopefully everything will be fine in the first time. So at the end, we just need to see this green V, and then we can continue to the next step. So the third step is the pins. So as we said, we have for each pin a specific metal layer. We'll probably have two, one for the powers, which are the highest metal, and different metal layers for the signal pins. So here we just need to enter the power pin names and the ground. And at the top part of the pins, I will talk about it in just the next slide. We need to know what metal layers our signal pins are, and we need to map them. So why do we need to map these? This is kind of tricky, and I'm not sure I understand it 100%. But first of all, if the pins are not in a pin type layer, then we can tell the generator to map them. If we wrote them in a text or in a label type layer, then we can just map them. And then the generator, he looks for all the things that are in M5 drawing and just converts them to be pins. So after we do this stage and we run this stage, we can open the abstract.pin view that is opened in our library manager and see that everything that was M5 drawing or M6 drawing, it's now a pin. And this is important for Slava to see that everything we have, all the stripes are actually the pins we want.
But this actually sounds a little bit worrying, because if you have, for example, a lot of routings on M3 and only 10 pins, he will expose everything, and
Okay,
I don't want to see it.
Yeah, I didn't add this here, but I think on the text boundary, one of these tabs, you can define on how many stages in the hierarchy it looks. So we don't change it. The default is 0, so it looks only on the top layer. And then everything underneath in M5 or M6, it doesn't convert.
Okay.
So I should mention this here so it won't cause problems, but you're right. It's supposed to look only at the top level, and then it doesn't make these mistakes. That's why I always say you have to open the abstract.pin view and make sure these things don't happen, because if we do, we have to go back and change them.
But actually, if somebody has some flat design, like a medium design, he will do it and everything will be exposed.
Yeah, doing it on flatten is a problem. Because the thing is that if I just add the M5 pins without the drawing beneath it, then nothing is really generated and we can't really connect to these pins. So I have to add the metal below it. And if we do flatten and it will look for all the drawings inside, yeah, it'll be a problem. I'm not sure how we can solve this.
No, I don't speaking about doing the flat deliberately. I speak about option that somebody does something small and does it from the scratch, and that's it.
Yeah.
So I think the methodology is unquestionably that you want to manually draw each and every one of your pins, how it should be extracted in the LEF. These should be on the pin layer and on the top hierarchy in your Virtuoso layout design, and then only extract those. I think one of the reasons for this mapping is that different PDKs will use different layer names and purposes and so forth, and so this allows you to kind of translate between them.
Yeah, exactly. That's what I wrote here, because I also encountered it in different technologies that in every place you write the pins differently. It may be label type or pin type, and this is just a way to map them. So maybe if we look at this layout that I added here. So I just add the pins from a layer of M3 pin, and I added myself this this drawing of metal 3, and it's in the top level. Underneath, we'll probably have a lot of other M3 stripes, but they're not supposed to be converted at this stage to also being pins.
Odem, I actually wanted to go back to this slide before because I don't know that slide you were on. I don't understand something here, and maybe the example doesn't look like I would expect. Usually, like the pin layer, and it's hard for me to see this resolution, it has like an X on it. And I would expect that if you want a pin here, it wouldn't be the actual text is something it's used, for example, for LVS, I need the text, but it shouldn't be translated obviously into the LEF in the end. But the pin layer should be, I mean, the metal 3 we have here shouldn't be a drawing. It should be a pin on top of a drawing, but I need the pin layer. Is this not this the way I see it here? And,
I think,
yeah.
I think, okay, this is not what you see here. I think here I just added, this is actually Romance, but it's, I do the same thing. This is a metal 3 drawing, but I think we can also make this just metal 3 pin, and then maybe in the pin stage that we're now looking at, just not convert the drawings. That's also a possibility.
Exactly. So from, and this I think answers what Slava was mentioning before. From what I understand, the methodology should be, you need the metal 3 drawing, or else you don't actually print out a piece of metal 3. But on top of the metal 3 drawing, where you want the actual thing translated into the left, you should have a metal 3 pin that is exactly on top of the area that you want to be exposed to the abstract generator, and you should not be translating any drawing layers. You should only be translating pin layers.
Exactly.
The X that you're talking about is there, you just couldn't see it.
Oh, okay.
Oh, okay. Yeah, so then we don't need to put here the drawing part, just M5 pin to M5 pin. It also works, and just make sure that there is a pin area beneath it. Yeah, I think that will work.
I think that's the correct way for you to control exactly what will appear in the LEF. As the layout designer, you can control what Slava in the end will see in the LEF.
Yeah, that could work. Okay. So here I mention again, when we finish the pin stage, we have to open the abstract.pin and make sure that everything will come out as we expect it. Okay, so the next step, which is also tricky, is the extract. So it just does the extraction of the physical of the block. Again, we always focus on the signal and the power stripes. These are only the metals that are important for the LEF file. These are the only metals that Slava cares about. So the first tab is the signal ones. So here we only want the layers of the signals, which is M5 in this case. These are the only ones we want to extract. All other layers are not important. And this also is only on the top level. So if it's with flatten, it will be very messy. And the second tab is the power one. Here it's metal 6. And from what I've learned from my ping pong with Slava, here we want to extract the power nets, but we don't want to extract the signal nets because it just generates a very heavy LEF and it's not really important. And the power nets we do want to extract because we want to see from edge to edge all our stripes. I think this is what solved our main problem with Slava. But then again, we have to open the, first the—
Wait, Odem, let me just again address that. And again, this is always tricky and I can't remember exactly how it works, and you obviously know better. But I believe that if you draw the pins of the power nets in the pin layer exactly what you want to be extracted, then you don't have to do that. In other words, this tells the tool, go and look for metal 6 and extract it. And you usually don't want to do that. You want to have complete control over what is seen in the LEF. So if you actually go and draw the power pin in the pin layer, you don't need to extract any of these nets.
Yeah, I guess I won't need to. This is just easier because most of the time the power nets are everything on metal 6, which is the power layer, I won't have anything but the power grids. So I don't mind doing extract for the power.
Exactly. So that's the case you'd use it. You never want to extract anything that's not on one of these top layers, such as the signal pins, because this means that the tool will always do something wrong and it will start routing things through your macro and cause shorts, which it shouldn't do, but it will happen.
Yeah. Okay. And the third tab, which is very important, is the antenna. There's not much to do, but just selecting all the calculations of the antennas, which is important details that they need when integrating the block. And that's it. We can just run this stage. And again, it's very important to see that the view that is generated. It's called the abstract.ext. There we can see all the signals and power nets. We have to make sure that they look good, that they're in the correct layer, that they're exactly on the boundary, and that everything is correct before moving on to the next stage.
So basically, to go back, I think that the first abstract.pin, it just takes the pin layers that you mapped and shows them, and abstract.ext takes those layers plus the ones that it looked for and extracted. And essentially, the best methodology is draw everything in a pin layer, then they should be the same. The abstract.pin and abstract.ext, or everything you need in the LEF will be an abstract.pin. If you want to not draw pin layers on all your power grid, for example, like Odem was saying before, then you should just have, the only difference should be the abstract.x will have the power rails on the top layer.
Yeah, exactly.
And regarding the antenna stuff, I would say even checking these things, it comes up every time. Search in your LEF file that you have the antenna information. Search for the word antenna and see that it appears, because if not, this can cause real big problems at the end of the chip implementation.
One more comment on, not on that, but on the LEF. I think it's actually important to sync with the place and route guide before doing the assignment of layers on for the macro, because, for example, in Virtuoso, maybe you use metal 2 on the left and right sides, and metal 4 on top and bottom, okay, for example. But in the place and route tool, could be a different assignment in terms of vertical versus horizontal routing tracks. So the tool might think that he favors metal 2 to be horizontal, but metal 4 should be horizontal too, because it's all usually HV, like interleaved. So if you assign it incorrectly, the tool will try to route to it with its horizontal attributes when it's actually is vertical in your layout, okay? So it's better to sync on the used layers. Beyond that, there are some grids for these layers. It's not a must, okay, because I understand that when you do a layout for a memory, for example, you cannot assign the pins on some grid because it's a replicated array. But sometimes if you have some wrapper and there are digital pins, it's better to prepare them aligned, because the job for the router will be easier and less probability for future DRCs and stuff. That's it.
I will even add to that with the power grid, if possible, I mean, you should always talk to, if you're not doing just a general thing that will be used somewhere, but you're using it on a specific chip, you should always generate the power grid according to how the top level plans to connect to it. And if possible, in some cases, you could even make your power routes at the same intervals and pitches as the top level, and it could even seamlessly connect to them.
Yes, exactly. Like sometimes we integrate it. For example, we have vertical M5 on top. So if your block is simple, we can tell you use this pitch and spacing and metal 5 and forget about it. We will connect like straightforward from the edges. As a natural native, we can tell you, wait a minute, you have a more complex block. We have metal 8 on top, so you can do your stripes on metal 7, and we will just connect it. Like, there should be some syncing between us, otherwise it will be harder to integrate.
Mhm. Okay. So this is the extract. And now we'll move on to the last phase, which is the abstract. It's the last one after. There's also another stage called verify, but we don't really care about it too much. So here, the first tab is adjust, and this is also not
I don't
quite.
know. Maybe you should be aware of this tab, because otherwise the ping pong between me and you not always as smooth as everybody. Everyone of us has different time constraints. So maybe there should be some verification on this.
It usually just passes, and if it doesn't, it's hardly things that you tell me, because it's not like the edges aren't correct or the pins aren't all the way to the bottom. So I can try to look at it again, but it never helped me.
Okay.
So here in the abstract, we have the first tab, which is adjust. So when we want to create we want to create the boundary pins, and this is what I've learned from your ping pong with the Andrada Slava, that she said something about the exposing all the stripes of the powers, and she found out that if we don't check this one, then it shows the whole stripe of the power and not just the boundary pins. So I'm not sure how this works. I haven't encountered it too many times. I'm not sure exactly what this does. I will look into it a bit further. But I guess we want to create the boundary pins for the signals and not to the powers. This is how it works for our last LEF files that we created. I'm
But
not sure.
the power pins are also boundary. Like they touch the boundary, right?
Yes, but I think that what happened with Andrada is that when she checked this, it only created the pin. She created like a pin at the boundary and then a whole stripe beneath it. And then when she did this, it created only the boundary ones, and
Ah,
the whole
okay, okay.
stripe didn't show. I
I
will try
understand.
this myself. I'll try this myself to see. But she said that this is what worked for her. It also works for me. I also run it this way. So I guess this is the way to run it. And if we'll ever have problems with this, we can look at this again. And then the next tab, which is also very important, is the blockage. So this is when we create the blockages of all the metals that we want to block for top integration. So we usually just want to create the blockages of all the layers that we have in our block, from the first layer until the power metal. So I guess it's until M6. We can just delete all the other layers and just check here the pin cutout, and it creates the blockages.
Uh, Regarding these cuts, I think this is only needed for the power, because the, if the digital pins are on the boundary, the
Mhm.
router will be able to access them even without the cut. Because I saw several times that these cuts actually cause the router to do weird stuff. When there are, for example, no track alignment, it could be do some crazy vias and do DRC. So these cuts do not help.
Okay,
At
so
least for the digital pins, if the digital pins are on the boundary.
yeah. Okay, so I'll try to generate a new LEF for you anyway that I need to provide you, and I'll try it with the pin cutout you just said.
One more thing, you mentioned here, like for 4 metals doing cover blockage. Does it means there is a single statement in the left with the blockage, or there beyond it there are multiple other patches? Because these patches like slowing down the tool unnecessarily.
I think I can change the blockage from cover to the other thing. I'm not sure.
No, I think that Slava, what you're saying is the other one is detailed. So I think cover means that it's one statement with this multi-rectilinear type of a thing, and detailed will put like real pieces and pieces and pieces
Okay.
where
Cool.
you don't have metals. So yes, you want cover on all but the top layer or something like that.
I think it should be everything except the power, because the power is have some cuts, so it's detailed. Others could be completely covered, and the router will be able to access from the edges.
So wait, you want here all the layers, the signal layers to be covered, but just the power layer to be detailed?
Yeah, I think so.
Okay, without, and all the others, they don't need the pin cut out, just the power.
Yeah,
Okay.
exactly.
So I'll try this now.
Again, it's I assume it should work, but I don't know for sure.
Okay, we'll try another ping pong. Okay. And these are the only things that are important for the abstract, just the two first tabs. And once again, we have a view that's created, which is called just abstract, and we have to open it and make sure that everything looks like it's supposed to. We can also check the blockages, that the routing blockages are created, and all the pins, of course, the power pin and signal pin, that everything looks fine before we create the final F.
So wait, do you hear me?
Yeah.
Yes.
Okay. So, for example, these green stripes and the yellow stripes inside, I don't need it.
This is not good. This shouldn't be
It's
there.
not good.
Yeah. Okay.
Beyond that, you see that the pins has some enclaves, some cuts on the edges, right? So if you do a cover there one page before, I think these cuts gonna disappear, but the router will be still able to connect.
Okay. Okay.
But this may have had like an extract or something on M2 and M3.
Yeah, this is just like an old example that me and Roman did a while ago. So I think
so this is not good.
Maybe there one macro and it's not an issue, but if you, for example, have several hundred of these macros, all of these LEFs are consuming a footprint of the memory, and maybe the router even considers somehow these lines. I don't know.
And it's also not clean, and it causes, hard to debug other things. You should see just one layer of blockage. And, and you should see your pins.
Okay. And that's it. The final step is just to extract the LEF, which is from file, export LEF, and save it wherever you want. And then you can see all your green Vs. And after exporting the LEF, we can open it and make sure that everything we wanted is here. So at the beginning, Adi also mentioned, you can see here that the class is block and not core. The origin is at 0, 0. The cell name is correct. You have the size approximately, and make sure.
Adi, what is this foreign? Do you know?
Which one?
The foreign statement.
Foreign?
Yeah.
I don't know, but it caused me and Udi a lot of trouble. I can't remember, but it it somehow gives an offset from the origin. Udi, do you remember? We screwed around with this.
Yeah, it was a mess.
I see it usually zeros, but I don't know.
It's usually zeros, but in certain standard cells, it's not, and it really caused us headaches.
So it's something with the overlapping of pair boundary, I guess.
Something like that.
Yeah. Keep it 0.
Keep it simple, right?
Udi, it's what you had with Matan?
What?
It's the problem you had with Matan?
Yeah, we struggled with it a lot.
Yeah, at the end, what I told him was just to move the origin, and it made some things change.
Yeah.
Okay. So I'm not sure exactly what it does, but this works.
By the way, here you can see that you can rotate your macro 90 degrees and it's not correct.
Yeah, here the symmetry.
Like in 60 nanometers, it's not correct.
Okay. Mine?
Yeah.
Okay.
It doesn't matter because I don't do it, but
Okay.
it's not correct.
It also probably is inside the abstract generator somewhere.
Maybe, yes.
Maybe. Okay. And that's it. Just make sure you have all your pins and they're at the correct layer. Also, Adi mentioned that you can also search for the word antenna and make sure all the antenna properties are there. And I think that's it.
I would actually say, Slava, correct me if I'm wrong, this almost caused SOC 2 not to be fabricated.
What do you mean? Ah, the antenna.
The antenna.
Because there was no antenna in the DML LEF, right?
Yeah. At the end, the tapeout was postponed for other issue, but it's also was.
Oh, we missed out on some DLC checks. Or we didn't check any antenna DLC or something.
Yeah, but because there was no antenna information,
No, because we were using an incremental to the DLC antenna file, I think, instead of the main DLC file. And then
what I'm saying is, if your antenna information is correct in the left, you should have no antenna problems at the end of placing.
Exactly, yeah. But we didn't know that until like the day we were supposed to push button on sending out the tape out. And then Slava, it looked weird for him that there were so little checks, I think, on the report. And then he dug in and suddenly he says, "Yes, Firsov, I think, does that make any sense to you?" And then all of a sudden, oh no, it's like we only use the incremental file for FFC, but the main antenna file is like, I think, from FF plus or something. And then we figure out, oh yeah, we have to have all those rules. And once Slava checked, we had like plenty of antenna violations.
Yeah. So
because one of the macro providers was not including the antenna information in the LEF.
Right. So that's very important to make sure.
The risky thing about LEF is that you encounter real problems very late, because LEF is an abstraction. And when we do a physical sign-off with GGS, we start some things starting to popping up, but the problem is it's 3 weeks before tape out, and then you, I don't know, tear your hair.
I just want to mention another thing if we already have this slide. So all macro owners should read their LEF, look at it, see. When you look at it, it says here some port layer M5, see that the rectangle seems to be, the right size, that it's not going in all kinds of weird places. Look at it. There's no reason not to. It's very readable.
Actually, maybe go even across the port, see that they touch the edges.
I would say show what you're going to maybe talk about in a minute, Slava. I don't know if Odem's going to say it, about loading it into Innovus.
Also an option, yeah.
I think that's important.
There is other tools to look at it, but Innovus is one option. But it's the problem with Innovus, you need some setup in order to do it.
So what tool do you have that can look at the left?
There is a K2 viewer, but it's not so easy to look there. Maybe there are other alternatives. I think there should be, because doing it with Innovus, it's an overhead.
You can look at it in Virtuoso. You can import LEF into Virtuoso, but it comes out of Virtuoso, so it's probably the same as the abstract that you see in Virtuoso. But it might be worth doing that, doing an import into Virtuoso and looking at it there.
Yeah. Like to see there are no redundant stuff, that the pins are touching the edges, stuff like this, like zero level verification.
Adi?
Yeah?
Since we're talking, do you know if we have we're working on a contract with Cadence beyond the existing one.
Jonathan, we're recording this and let's talk about that after. I saw you
Right.
sent an email.
All right.
Or you just edit the video. You open LCD.
I'm not editing this video.
Never mind. It's okay. Yeah, I'll just email my reply to you there.
Yeah. Okay. Odem, you have more?
No, that's it.
Okay, Slava, maybe even with the document you once made, do you want to go over some more perspectives from the top level? I mean, you probably mentioned a lot of them during the talk, but maybe you can show it with some pictures too that you already prepared once.
No, I don't have anything prepared yet.
Okay, so I think that if I want to summarize, there are a few things that we have a document, right, Odem, that is a tutorial that shows all the things that you showed in the abstract generator, what to do. And even though this is often what happens is people, don't do the RTFM, they don't read the manual. There are little things that are really important to make sure, the different buttons, and maybe Odem, it's worth going over the document and updating in case we found out things like what Slava was saying about the pin cutout and the methodology I was mentioning about drawing the pins and so forth. Because
Yeah.
we have a very detailed document, correct?
Yes.
Okay, so really work with the manual when you make your abstract. The important thing here is to really open up the LEF, both the text, and probably import into a viewer such as Virtuoso or the K2 viewer or into a Novus, and look and see that what came out is clean, that it looks like you have what you wanted to have. The pin that the router is going to see is the pin you wanted it to see. It doesn't see anything beyond that, and it for sure sees what it should see, including like the pins at the borders, the power layers showing the powers where they're supposed to connect the whole pin, not just a part of the pin, but not showing power layers that are down below, having blockages at the layers that you don't want to route through your macro. These things are very important. In the lib file, you want to make sure that your lib file, you understand what it says and it covers how your functionality is. And really, if you're doing it for a first or even probably a second time, ask people who have experience with this and have done it before you start sending these things to Slava or Rinat or whoever you're dealing with.
Actually, this picture on the slide is a perfect example that the pins do not touch the edge. If you look for the clock, for example, the clock pin, you see that its Y value, sorry, the X value, the last one is not 295.92. It's a little bit less, right?
Mm-hmm.
So it doesn't touch the edge.
I would say in the presentation, there were a bunch of pictures that are all bad examples. So I think we should really maybe even make a version of the slides where we have the bad example and a good example of such a thing and point these out, because that would really show people what they keep doing wrong and Slava has to ping pong about. So
Adi,
yes.
hi. I have a small, simple question about antennas. We took in lectures about LEF files and antennas, but we didn't get into it like deeply. I didn't get it.
Okay, I'll explain. So first of all, we learn more about antennas in the course that you didn't do, the VLSI or integrated circuits course. Antennas basically means that when I am manufacturing the chip, if I make a specific layer, so usually you make the transistors, then the contacts, metal 1, via, metal 2. If you are actually so you do it in that order. So part of the chip is already processed and there, and then you go and deposit the next metal layer. When you deposit the metal layer, there's like a charge that builds up, and it's stuck there because it has nowhere to go. And if enough charge is deposited, similar to static electricity, when you touch somebody and you get like an electric shock, it will build up so much voltage that it will break the oxide of the transistors and burn out the chip. So this is something that has to do with the amount of metal layer at a certain, that is not grounded through something that can be grounded, versus the amount of oxide there is there that will be burned out if too much charge is on it. It's a ratio that says you count the amount of metal layer during a certain process step divided by the amount of gate, polygate that it's touching. If it's higher than a certain number, then that is a violation. Okay, so it's something that's very technical.
Like to absorb the extra charges and like that?
Yes. So if I have a little bit of metal and a big gate, it won't burn it out. But if I have a lot of metal that's not grounded through any other way, and it's touching one little tiny minimum transistor gate, it will probably, there's a good chance that during manufacturing, it'll burn out the gate. So I don't want to ever come near such a thing, and there are ways to get around it. For instance, if I just add a diode, a reverse bias diode, the reverse bias diode will break down before the metal gate, and then that's fine because it doesn't get ruined. It just brings the charge to ground. So that's something that we can do, or you can just change the routing a bit by going up or down a metal layer to change this ratio. It's really easy to find out. The problem is that when we make a LEF file, we don't see the gates even. We don't see all the metal layers that are made underneath the LEF. The LEF is an abstract. It takes away from the router, so it doesn't have to see everything that's inside. So what we have to do when we provide the LEF is tell it what the numbers that are relevant for calculating this ratio are. Okay, so that's why we have antenna information inside the LEF.
To build on what Adi had just explained, so this is known as, in the fabrication world as IPC, in-process charging. So the mechanism is just like Adi said, it's damage due to the charging of the interconnects during the plasma processing steps in the back-end layers. So you get charge that is accumulated on the metal lines that act as antennas or as collectors. So what happens is you have voltage that is generated and accumulated. You have accumulated charge that can potentially discharge through the gate, the gate oxide. So that's the physical mechanism.
So it's really easy to not cause antennas, but if you're not aware of it, they will be caused because you're making all these routes with you don't care about any type of thing like this. And if you don't check it, it's going to be caused. So inside the LEFs, you just lose the information there. And so you're routing at a higher level, you're connecting to these blocks, and you're causing these violations by mistake because you don't know that there's a problem underneath. So what you have to do is when you make the LEF, you don't only abstract away all the metal layers inside, you also abstract away this antenna information just by putting one of these sentences like antenna partial metal area that you can see here inside the thing. I don't even know what these things exactly are. You can look in, of course, the LEF user manual to understand what they are. But anyway, it tells the router, listen, when you calculate your ratio, add this and this number to the ratio, and then it will figure out if it needs to route differently or maybe add a diode or something like that. Because in the end, we'll run our DRC check and we'll see this. We'll see that there is this violation, but it's too late because we've already closed up our macro. We don't want to make any of these ECOs, these changes at the last second when we already have our GDS out. We want to do it while we're routing.
So yeah, to take it into account, like to solve the problems
exactly
with these,
when it's easy to solve and not when it's hard to solve.
Yeah, got it.
Okay.
I think the most important statement is at the end, during physical sign-off, we will find all the problems, but the problem is it's too late. So we try to find them earlier and solve them earlier.
And it's worth noting this is totally process dependent. So this is due to the nature of the materials that are used, in the metals and the gates themselves.
Right. So in this case for the router, the tech file should have the information of what this ratio is that should be checked. And in the
Right.
DRC rule deck, there's a special rule deck that all it does is check this antenna stuff. And that's per PDK, per process.
Right.
Okay, so I think that was very nice. Thank you, Odem and Slava and everybody for your input. And again, I will upload this to the web, and at some point we should actually update and make it more extensive, and maybe in the second semester class I'll have time to do that, and we'll make it more methodological. Okay, so great. I hope whoever needed that learned things, and I hope it causes less ping pong and less problems. And good. All right. Odem, can maybe
a session on lib files?
What? And
maybe also a session on lib files. For me, it would be actually very good to learn a bit.
Yeah, actually, me and Esteban did this at some point together, right, Esteban?
Yes.
So probably when we find time to prepare an incremental version of this, we can also make a fuller version of the lib files.
I will be grateful if you can do this, because I always feel like I'm totally lost when I go and I just do stuff like monthly.
I mean, lib files are very, 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 very complex, but the stuff we need from them is not that complicated. It's just trying to understand it. Actually, Odem said at the beginning, the most important part is the LEF. No, the most important part is probably the lib. But the LEF is supposed to be the easy part. It's just because the tool's pretty outdated, it becomes a pain.
No, for us, what we did is, except for Odem, is we by design took all the content of the lib and made it irrelevant.
Mm-hmm.
So we only care in this project. We only care from the lib is the name of the pins.
Right. So that's something that's good to do in a research project, but often it's not good on a production level.
It gets much more complicated when you actually need to close timing on the custom circuits. And
I actually discussed some of this stuff with Anatoly on a product not long ago. So this becomes very relevant, and it's not well taken care of in general in industry either. So, I mean, for memories it is for sure, but for other blocks it's a difficult thing.
Then you can totally ignore the lib file and build the LEF based on Verilog, by the way.
Yeah, but you need the lib file for integration in the end in any case.
Yes, so if you need it, then...
as far as we know, I haven't heard anything different from Slava, but you cannot do init for the, or I don't even know if in synthesis you can always include the netlist. But if you need to include the hard macro in your place and route tool, it would not let you do it if you don't have a .lib.
Correct. Yes. Maybe ILM could stand instead, but it's an even more complicated thing.
Exactly. No, you need the lib and the LEF. There's no question.
But I think the way we're doing it right now is like pretty simplified and the minimum integration work that the macro provider needs to do in terms of lib writing.
Yes. But as Roman said, we should actually have a talk that shows how to do this in a more methodological way.
Would that not include actually running what's the name of the tool?
Liberate?
Yeah.
So again, that's hard. So I think that just to explain how to manually do it and then say,
but I mean, if you actually have, if you actually design a custom circuit that needs to be part of timing past. So it need to you need to integrate it and then create timing routes with the higher levels. Then do you do it manually? I mean, I know that you do it with
Unfortunately, I
the
will tell you that I think that in a lot of cases, and this is again speaking to Anatoly, that is done still for most analog blocks manually and trying to be by design as high margin as possible. But there are tools to do it. They're just very hard to ramp up.
but it's really then in that case it's quite suboptimal.
Yeah. So a lot of people will write their own script, and
Right.
it's
Okay.
not that hard to write the script, even though the lib language is quite
Fair enough.
complex.
Yeah, that makes sense. Okay.
All right. So thank you, everybody. I'm going to stop
Thank
recording
you.
now.